Welcome to ATMOS 5000, Day 16. Our objectives are being pulled from the Stull textbook, Chapter 6, specifically Sections 6.1, 6.2, and 6.3. We're going to investigate what happens when you mix two air parcels together, and we'll come up with something called the linear mixing rule. We'll talk about how clouds are classified, and then we'll talk about how clouds do some self-organization into cloud streets, open cells, and closed cells. The linear mixing rule basically is trying to describe what the product of a mixture of two air parcels will be. So in this example, we have parcel 1, which happens to be smaller than parcel 2. And we add those two parcels together, we thoroughly mix them, and we come up with a larger air parcel that has the thermodynamic properties that are a weighted average of the thermodynamic properties of the individual parcels that made up the mixture. So if we look at the temperature of the mixture, it's going to be the mass of parcel 1 times the temperature of parcel 1 plus the mass of parcel 2 times the temperature of parcel 2 divided by the total mass of parcel 1 and parcel 2 put together. The linear mixing rule can describe the thermodynamic properties of mixtures of air parcels, and those thermodynamic properties extend beyond temperature. So here we have an example of the water vapor pressure E, the absolute humidity rho V, the water vapor mixing ratio R, and the specific humidity Q. And the linear mixing rule obviously can be expanded to include the mixture of more than two air parcels. And if so, you would just extend it M1 E1 plus M2 E2 plus M3 E3 divided by the sum of M1 plus M2 plus M3, etc., etc. So the cloud classification is based upon the visual observations of the clouds. And the two most obvious visual observations associated with these clouds are the height above the ground and the shape, whether it be cumuliform or stratiform. A tertiary cloud classification is whether or not the cloud happens to be precipitating. So based on the height above ground level, that's the first thing I look for when I'm trying to classify a cloud. And is it a low cloud, which is typically within about 3 kilometers of the surface? Is it a mid-level cloud between 3 and 6 kilometers? Or is it a high-level cloud above 6 kilometers? Or is it deep, extending through multiple levels of the atmosphere? And it should be noted that these ranges for low, medium, and high are somewhat subjective and are latitude dependent. For example, because the troposphere changes height dramatically between the equator and the poles, the definitions for low, medium, and high clouds have to expand as you move towards the tropics. And then on the cloud shape, we have our cumuliform and stratiform, which we will be defining next. So we have our basic cloud shape, and these cloud shapes are based upon what we call the aspect ratio of the cloud. The aspect ratio is the ratio of the width to the height. And over here on the left, we have our cumuliform clouds, which have an aspect ratio of approximately equal to 1, which means that the width is typically about the same as the height. And that is very distinct from stratiform clouds on the right, where the width is much, much greater than the height. In this case, we often refer to stratiform clouds as layered clouds because they will often cover much of the sky, but yet persist in a relatively shallow layer. So here we have our cloud classification naming conventions. What we do is we take the different height categories, low, mid, high, and deep, and combine those with the shape, either stratiform or cumuliform, in order to come up with a basic name for the cloud. So for example, a low stratiform cloud would be referred to as a stratus cloud with the abbreviation ST. A low cloud that exhibits cumuliform features would be a cumulus cloud, abbreviated CU. And these low clouds, there's a third category that's basically a combination of stratiform and cumuliform. They are cumuliform type clouds, but they're close enough together to where they cover most of the sky. And from underneath, it's essentially a layered cloud with light and dark patterns where the thickness of the cloud varies. And we refer to those as stratocumulus clouds. They're very common along the west coast of the United States or near the cold ocean. And the stratocumulus are often top these boundary layers that are over the ocean, over a cold ocean. Then we have mid-level clouds. The prefix that we use to describe them as mid is alto. And then, putting that together with the shape factor, we have altostratus clouds, AS, and we have altocumulus clouds, AC. The high-level clouds, the prefix that we have for high-level clouds is cirro. And so our combination of cirro and stratiform would give us cirrostratus clouds, CS. And cirro plus cumuliform clouds would be cirrocumulus, CC. And there's a third variety of high clouds, which are just known as cirrus clouds, and they're thin and wispy, and they don't really conform to either the stratiform or the cumuliform descriptor for cloud shape. And then lastly, we have deep clouds. Deep stratiform clouds are referred to as nimbostratus, and deep cumuliform clouds are referred to as cumulonimbus. We often just call them CBs for short. And both of these have nimbo or nimbus, which is essentially a Latin root that refers to precipitating clouds. And these clouds are precipitating in part because they're deep. So here we have a visual representation of the different cloud types. We'll start low and work our way up. On the bottom left, not the extreme left, we have our stratus clouds, which are layered clouds near the surface. They have very few features. They're very difficult to get a picture of because they're featureless and they often blend in with the horizon. Then we have our stratocumulus clouds, which are kind of a combination of the cumulus and the stratus. They fill most of the sky. And then we have our relatively small, modest cumulus clouds, which are low clouds as well. Interestingly enough, the size of the cumulus convection, other than cumulonimbus, the elements are about the same size. And so if we have mid-level cumulus clouds or low-level cumulus clouds or high-level cumulus clouds, the convection is actually about the same dimensions. But as you move further away from the ground, the clouds actually appear smaller because they're further away from the observer. And that's one of the cues that we use to distinguish between cumulus, altocumulus, and cirrocumulus. And in this image, you can actually see that as you move higher in the atmosphere, the cloud elements appear to be getting smaller. But in reality, they're the same size. They're just getting smaller from the perspective of a ground-based observer. With the altostratus clouds, they cover the entire sky or most of the sky, and they're thick enough to where they actually block out most of the direct sunlight. In altocumulus clouds, you can usually kind of tell where the sun is. It's a bright patch in this layered cloud, and sometimes you can actually see the sun directly through the clouds, and you can look at it with your eyes without any harm. And the way you can tell the difference between altostratus and cirrostratus is that cirrostratus clouds are much more transparent, and they let a lot more of the sunshine through, but they also are associated with a halo, an optical effect around the sun, which is based upon the ice crystal structure of the cirrostratus clouds. Over on the bottom left, we have our nimbostratus clouds, which is a deep layered cloud. Because it's deep, it's able to form precipitation, and it generally produces light but steady precipitation that can persist for hours. And that's as opposed to the cumulonimbus or the CB cloud over on the right, which is deep. It's got really strong updrafts. It can produce really intense rainfall, lightning, tornadoes, gust fronts. All of those sorts of things are capable of being produced by the cumulonimbus clouds. And then up at the top, it has an anvil that is basically defining the top of the tropopause. And then in the very center top of this image, we have the cirrus clouds, which are thin, wispy clouds, which don't conform to either the cumuliform or stratiform descriptor. cloud pictures. There are lots and lots of websites where you can see pictures, examples of these different cloud types and different cloud genre. And we will be looking at some of these websites in the in-class activities in order to get a better, more practice at being able to describe the cloud names associated with what we see visually. So talking a little bit about the organization of clouds, on the left we have a beautiful picture of cloud streets. And you can see why they're called cloud streets, because they have these linear features in their nature. And one of the factors associated with these cloud streets is that they form parallel to the wind vector. So in this case, the wind is moving from the observer out away from the observer, and with a slight curvature associated with that. What's actually going on here, if you look on the right, is that these clouds typically are happening in the boundary layer, and we have what we call rolls that are formed transverse to the direction of the wind flow. And on the upward segment of these rolls is where these clouds are actually forming. And then on the downward segment of the rolls, the clouds are essentially evaporating, and you have ascent where the clouds are at and descent in between. It's a fairly stable situation, and these cloud streets can persist for a long period of time. We also have open and closed cell clouds that are grouped together. So with closed cell clouds, the clouds are essentially filling the interior of the cells, and you have essentially white space, or in this case, cloud-free area around the individual cells. With an open cell, it's the opposite. You essentially have an area without clouds in the middle, and around the periphery of the cell, you have cloud formation. I'll give you some examples of this. So here we have a satellite image of a cloud deck, or essentially clouds over the ocean, and the white elements are the clouds and the dark areas are essentially the transparent areas where you can see the ocean underneath. And so the question is this an example of open or closed convection? When I look at this example, what I happen to see, what my eye is drawn to, is the edges of each of the cell, and with essentially a clear area in the middle. And so that's a good example of open convection. Here we also have an open cell convection. You mostly have the white space around the periphery of the individual cells, but it's a little more complicated than it is in the image at the top. So let's take a look at this particular cloud deck. Is this one open or closed? Well, when I look at this cloud deck, what I see are the central elements with essentially clear areas around the edge. And that to me is an example of a closed cell convection. And here we have an animation of closed cell convection where you have elements that are in the center, the convections in the center with the clear areas just around. Specifically in kind of the bottom center of this, you can see the convection that is moving up and the kind of little bit of clear areas around the edges. It's an example of closed convection as well. Open or closed? Well, when I look at this one, I kind of see both. There's certainly in the bottom right-hand part of the cloud of this image, there are definitely open cells. I look in kind of the upper portion of this and I see a lot more closed cells than I do open cells. So here's your open cells, and there's examples of closed cells.